Welcome to 11.1 Electric Forces and Fields. Now, we have already dealt with electric forces within the last chapter. Force is just a push or pull acting upon an object. And so when we take a look at an electric field, taking a look at this idea of a field is really just a sphere of influence. A sphere of influence. Okay, and when we talk about an electric field, if we're talking about an electric field around a point charge, we're going to use this big capital E is equal to KQ over R squared. Now this is very similar to our force formula, minus 1Q. And that is because we've got a charge that is generating a field. We use the absolute value sign here because that field can be within any direction. A second formula that we can take a look would be the force that is exerted upon a charge divided by the charge that is there. So I'm going to call because we've got two Q's here and it shows that way on the formula sheet, I'm going to emphasize this one as this Q being the charge generating the field. Charge generating the field. And so that, of course, would be in coulombs. Where this secondary charge, we'll use green there, this is the charge in the field. Again, measured in coulombs. So K, Coulomb's constant, and we did that in chapter 10. R is the distance from the point charge. Okay, meters. And so our electric field strength, right, the sphere of influence around charged objects is our electric field strength, is going to be in newtons per coulomb. Now, the direction of electric field is always the way that a positive test charge would move within that field. And so if we just take a look at, let's say we've got a positive charge here. This is going to generate a field that's going to interact with all electric fields around it. But if that charge were positive, that would move away. And so it would look something like that. Whereas around a negative charge, we would see a similar pattern, but everything would be pointed towards it because positive test charges would move towards the negative charge. And again, it's just that sphere of influence. So if we take a look at our first example, finding electric field strength from a 1.5 meters away from a 1.5 millicoulomb charge. Okay, we just want to know the electric field strength. And so KQ over R squared. So we're going to plug in the numbers. Coulomb's constant be 8.99 times 10 to the 9. We got 1.5 millicoulombs. Milli, it means times 10 to the negative 3. All over 1.50 squared. And so as you get that, you should find that you get an answer of 5.99 times 10 to the 6 newtons per coulomb. Now again, we're talking just about the strength. This is a scalar quantity because if this were our charge here and it was 1.5 meters away, well, that would be an electric field strength moving to the north. Where if it was 1.5 meters away here, it would be going to the south. If it's here, it's kind of going southeast, right? Depending on where that 1.5 meters is in relation to the charge, and the nature of this charge, and the nature of the charge in the field will dictate the direction of the force. Just the charge generating would be there, but we don't know if this is necessarily even a positive or negative field of charge. Let's take a look at example number 2. We've got electric field strength where a test charge experiencing this much newtons. Well, this is a case where we're going to use the second formula. And it's not just because we've got a force and a charge, but this formula is, again, this is the force experienced by a charge in the field. Force on charge in the field. Okay, and so this one here is the charge in the field. And even though they're both Q's, it is an important distinction for us to be making. And so plugging in our numbers, we got the 2.60 times 10 to the negative 3 newtons divided by 3.00 times 10 to the negative 6 coulombs means that the electric field strength is going to be 867 newtons per coulomb. Okay, in our third one, we've got what is the electric field strength here between, or the electric field between an alpha particle and a proton, where the centers are 1.0 times 10 to the negative 7 meters apart. So if we think about this, we've got the alpha particle sitting here, we've got the proton sitting over here, and this is 1.0 times 10 to the negative 7 meters. The point that we're looking at is the midpoint between, which would be 5 times 10 to the negative 8 meters away from the alpha particle, and 5 times 10 to the negative 8 meters away from the proton. So it'll look something like this. Okay. In this case here, because we've got kind of two relative points, we're going to see that the alpha particles now, positive things are going to be pushed from the alpha particle towards the right and away from the proton towards the left. However, because the alpha particle is twice the charge of the proton, we're going to see a much stronger field going right than left. So in this case here, we do need to know the charges. This is where our formula sheet can come in very handy, because we see we've got an elementary charge of 1.6 times 10 to the negative 19 coulombs, and an alpha particle is 2 times that elementary charge, and a proton is 1 times that elementary charge. So from the we'll use purple here from the alpha particle. Okay, the electric field, Q over R squared. So we again use Coulomb's constant, 8.99 times 10 to the 9. The charge is 2 times that elementary charge, so it's 3.2 times 10 to the negative 19 divided by 5.0 times 10 to the negative 8. All squared, and you should get a value of 1.15 times 10 to the 6 newtons per coulomb. Okay, let's use blue for the proton. Okay, and we're doing the same thing. And so 8.99 times 10 to the 9. The charge on the proton, however, is half that amount. It's 1 times the elementary charge divided by the same distance, which gets you a value of 5.75 times 10 to the 5 newtons per coulomb. Now, in this case, this is going, based on the drawing, towards the proton to the right. This one is going to the left, and so they are acting within opposite directions, and so we are going to be subtracting those two, and so the total is 5.75 times 10 to the 5 newtons per coulomb. And based on our diagram, we would be saying right, although we don't know that this is in fact the actual relation. But in between, we know that's towards the proton. Right, so it doesn't matter whether the proton is here or whether the proton is here, it's still going to be towards the proton, as these sources are moving out in all directions. Okay, give this next one a little try here. Pause the video, give this a try, and let's see how you do. Okay, as you've gone through, again, we're using our electric field formula, but we're going to be rearranging it for R. First by multiplying both sides by R squared and dividing both sides by the electric field strength, and then square rooting both sides. Gets you an answer of 38 centimeters. Now, just by comparison, because we could also have a gravitational field. If we were to take a look at the gravitational field between the proton and the alpha particle that we had previously done, that electric field is going to be Gm over R squared. The G is fundamentally different. That G is 6.67 times 10 to the negative 11. And the masses of an alpha particle, again, found on our formula sheet, right here, and the proton right here. So 6.65 times 10 to the negative 27. Divided by the radius, which we knew to be 5 times 10 to the negative 8, all squared, gets you a gravitational field strength of 1.77 times 10 to the negative 22 newtons per kilogram, and that would be towards the alpha particle because gravitational fields are always attractive. The other side, we're doing the same thing, except we're using the mass of a proton. And in this case, it's going to be 4.45 times 10 to the negative 23 newtons per kilogram, again towards the proton. Now these numbers are quite small, still acting opposite directions, and so for a gravitational total, you'll wind up with 1.32 times 10 to the negative 22 newtons per kilogram. And again, we can't really say to the right or left because we don't know the orientation of the alpha particle and proton, but we can say this is towards the alpha particle. Sometimes you're going to be asked to draw sketches. Key thing to remember here is electric fields are always going to be the way a positive test charge would move. So On the outskirts, this is going to be relatively easy. It's going to look something like this. But in the middle, what you're going to see is sort of a bending. It's going to look something like that in order to have electrons. The things that are slightly closer to this electron on the left are going to bend in towards the left. Those that are closer to the right, one on the right, are going to bend in slightly towards the right. Now similarly, I know this is not part of the actual question, but if you were to do it between two positives, you would see those same sort of lines. It's just that those arrows would be pointed in the opposite directions, and that is simply due to the fact that it is the way a positive test charge would move. Okay, thanks for watching. If you do have any questions, let me know, and have a great day.